This series of lessons will provide you with an overview of the various techniques that may be employed to maintain the stability of the drilled shaft excavation during the entire construction process, from drilling the hole to completion of concrete placement. The stability of the excavation is important for construction safety, to avoid potential impact on adjacent structures, to maintain the integrity of the bearing formation, and to provide structural integrity of the completed drilled shaft. A variety of techniques can be used to maintain stability, but the basic requirements are typically dictated by the characteristics of the subsurface materials, as well as the groundwater conditions. This is why it is so important that the contractor have good geotechnical information with which to plan the construction techniques, as was described in the lesson on geotechnical information for drilled shaft construction. It's imperative that this information be reviewed by the entire construction team so that the contractor can develop an effective installation plan which will maintain stability. The tools and equipment needed to excavate the soil and rock will also influence the techniques used to maintain stability. And so there are a variety of factors that must be considered. Some ground conditions are inherently stable and allow excavation of the hole for drilled shaft construction without the need for additional support. These conditions are typically limited to dry soil with little or no seepage into the hole, strong, cohesive, or cemented soils such as stiff clay, marl, caliche, or cemented sands, and intact rock. However, the rock itself might be stable, but the techniques that may need to be used to excavate it can impact the stability of the overlying soils. Of course, the relative strength of the soil needed to provide construction stability depends on factors such as the diameter and the depth of the hole, the loads on the ground surface nearby, potential vibrations during construction, could be, for instance, from trains moving nearby, or other construction equipment, and the length of time that the hole must remain open. Local experience often provides a good guide, but does not eliminate the need for site-specific geotechnical information. Many developed areas of the southwestern U.S., for example, parts of Texas, Colorado, Nevada, have conditions which are conducive to open hole excavation, and in such conditions, drilled shafts can be constructed very economically. When stable conditions cannot be assured throughout the extent of construction, temporary steel casing is one common method that may be employed to provide stability. In the case shown in this photo from a site near Atlanta, Georgia, the portion of the excavation extending through the cohesive overburden was performed as an open, dry hole, after which a casing was installed to provide lateral support to the borehole wall during excavation into the harder and more granular decomposed rock and harder rock materials below. Perched groundwater was present just on top of the underlying rock, as may often be the case where drilled shafts are installed to a harder and more competent bearing formation. You can see the service crane setting the casing into the hole, and then the drill rig can be used to twist it and seat it into the bottom of the hole. This can help seal the excavation into a deeper, stable formation so that construction can then be completed in a dry, stable, and supported excavation. Sometimes a contractor may even use multiple casings with a shorter surface casing followed by a smaller diameter inner casing that extends to the rock or bearing layer, as you see here from a project in Texas. You can see that the bottom is dry from the sunlight being reflected onto the bottom by a mirror, common inspection technique. In situations where the overburden may not be stable, casing may be advanced ahead of the excavation. This photo shows a casing advanced using a vibratory hammer a method that works quite well in sandy soils. After concrete placement, the same technique would typically be used to extract the temporary casing. Sometimes permanent casing may be installed this way, such as for this transmission line project where really large diameter drilled shafts were used and extended through very soft and unstable soils. The casing in this case was utilized as a part of the structural strength of the drilled shaft. The casing may be used without a seal into a strong layer if the hole is filled with water, as in this project in Utah. The casing was elevated to maintain a fluid head above the groundwater and thereby prevent inflow. In this photo you can see that the concrete placement is in progress, with the concrete being pumped into the shaft and the water being pumped away, and an oscillator machine is used to twist and extract the segmental casing. A lot more information explaining the different ways to use casing will be provided later in this series of lessons. Some types of permeable rock or cemented materials may provide inherent stability even below the groundwater. Examples include porous limestone or permeable sandstone. In general, it's desirable to add water to the hole during excavation of such materials rather than to allow flow from the ground into the hole, which can bring fines in or cause sloughing in weak layers. Although cohesive soils with low permeability may appear to provide a dry excavation, it's important to anticipate the requirements of subsequent strata. For example, advancing a dry excavation through a clay soil into a water-bearing sand stratum could result in flowing sands or bottom heave if the groundwater level in the sand is higher than the base of the excavation. Unstable sands at the bottom of the casing can result in flow of sand up into the casing, causing ground subsidence around the hole and loosening the soils around the drilled shaft. Another means to stabilize a drilled shaft excavation is with the use of drilling fluids within the hole. Fluids can include water or water mixed with minerals, typically a bentonite clay, or water mixed with synthetic polymers. Fluids can help to provide stability by counteracting the head pressure of the groundwater that would tend to flow into the hole, and we've already talked about drilling underwater to avoid inflow. Water may be sufficient if the soil or rock is relatively stable. In this case, the waterhead avoids the tendency for inflow, which can destabilize the formation, as well as to flush fines into the hole. Fluids such as mineral or polymer slurry also provide some support by the differential head pressure when the fluid head within the hole is greater than the groundwater pressure in the soil. An excess head pressure of 10 feet or more within the hole, above that of the natural groundwater, is often sufficient to provide stability through granular soils. The addition of minerals or polymers is used to help contain the fluids within the hole, minimize fluid loss through seepage out of the borehole wall, and thereby maintain this positive head pressure. So in our next segments, we'll talk in more detail about the use of fluids and casing to maintain stability. But first, we're going to talk briefly about some fundamental principles from soil mechanics that are related to the stability of an excavated hole.